In this course, I have the goal for you of being proficient with Boolean algebra. And so to become proficient, you have to start with the basics. And this first slide talks about properties associated with one variable. Okay, so for example, there's this identity property. And the way this graphic is set up, these are cards that flip over. And so what I'd like you to be able to do is to look at the identity and then name what or look at the term and name what that property would be. So let's do the first one. We click on this to reveal the identity, Boolean identity. That's kind of redundant, but that's the way it is. So the first one is A or A is equal to A. And the second one, based on the and, is A ANDed with 1 is equal to A. So why the name? The name is called identity. So you flip that back over. The name is called identity because the output is identical to the input. Okay, so you're doing an operation with zeros or 1, depending on whether it's or and you get an operation that's the identity. Okay, the next one is null. All right, so null, if I do A or 1, I think that's fairly obvious. The 1 dominates. No matter what A is, you're going to get 1 as the answer. And if you have A ANDed with 0, no matter what A is, 0 is the answer. So this is called null because the property does not depend on the variable at all. It's nulled out. There's no A showing up in the output here. All right, so that's another single variable property. Okay, the next one, idempotent. Okay, so in this case, you're doing an operation on itself. Okay, so A, all right, that's the self. The operation is or, so A ORed with A is A, and A ANDed with A is A. Okay, I think this is a relatively obvious identity, but that's the name of it, idempotent. Okay, and so next on the list is complement. All right, this is something that doesn't show up in regular algebra because it just doesn't. All right, so with complement, what we know is that when you take the complement of the variable, if you OR that back on, A ORed with the complement gives you the whole realm of possibility. So A ORed with A bar is equal to 1. I think it's pretty easy to see with a truth table. On the other hand, if you do A ANDed with A bar, then that forces one of these to be a 0. 0 ANDed with anything is a 0. And so that identity is obvious as well. Okay, involution, I think, is an obvious property as well. So with involution, we just apply the complement to the complement. All right, so if you do a complement to the complement, you get back A. So complement is its own inverse. You apply it twice, and you return to the start. Okay, so those are some of the basic Boolean identities. The next thing you need to know about Boolean identities, I think, is the duality rule. It turns out that what you can do with all Boolean identities, okay, an identity is just where you have two sides of an equation and they're equal. Okay, so if you swap all the ORs with ANDs and every 0 with a 1, then you keep the identity. All right, so let's start with the identity. All right, so A ORed with 0, if I swap the plus to an and the 0 to a 1, I get back the original, or I get also a true identity. Okay, so idempotent, A ORed with A, if I swap the plus to an and, all right, there's no zeros and ones in this one, I get that the same, I get a valid identity. So this happens not just with these single variable identities, this happens for any Boolean expression. So that's an interesting property, and it helps make this complementary version of digital logic that we will see when we do, for example, SOP forms and POS forms. There's this complementary symmetry that you see with digital logic. Okay, next up, basic Boolean identities that apply to more than one variable. So we know about regular algebra, Boolean algebra has similar identities. There's the commutative, so the order of operations doesn't matter. There's associative, where you can do, if I have three things I want to OR together, it doesn't matter which order I do the ORing in. And then there's some that look a little different. There's absorption. Okay, so A ORed with A ANDed with B. It turns out, the B part doesn't matter. This gets absorbed into A. You can do a truth table to prove that. So that one's a little less familiar to you. And by the way, you can show the dual of all these properties. Okay, if you do the AND version, you would get the same types of properties that you get from before. Okay, so over here with distributive, there's a form of this that just looks wrong. All right, not this one. If you do the AND form, A distributed across, that looks like regular algebra. But if I show the dual, all right, A or B ended with C, that's just not familiar looking to us. But this is actually the distributive property applied across the plus sign. So there's no decimal equivalent of that. I said decimal. Regular algebra is what the word should be. Okay. You can also verify this by a truth table, and you can do the columns. You have A ORed with B and C. So this column is here, and then it matches this column. So you can see that it's a valid identity. Okay. So the other thing that I want to talk about, which is important, is De Morgan's theorem. All right, so we talked about this before in the jump start or the quick start video. But if you take the complement, I'm taking the long bar across here. That's why I like the bar notation. If I take the long bar and I break it, I want to find what the answer is. And a lot of times, this happens every semester, students will assume that A or B with a bar over it is the same thing as A bar or B bar. And that's not right. Okay, this is actually even more common. A, B with a bar over both of them is not A bar ended with B bar. All right, so if you want the real rule, it's when you break the line, you change the sign that connects them. Okay, that's De Morgan's theorem. Break the line up here, change the sign. Okay, another interesting way to visualize this that is very useful when you start to do schematics is that you can essentially visualize pushing an inversion bubble through a gate, and the gate itself will change from AND to or to AND. Let me show you what I mean. Okay, so in this next illustration, I have a NAND gate. All right, so I think it's pretty intuitive that a NAND gate is AND with an inversion. All right, so we often use bubbles for inversion. All right, so here's an AND with an inversion. If you applied De Morgan's theorem, A ANDed with B with a bar over the top, this turns into A bar or B bar. So if you push the bubble, visualize pushing this bubble backwards, it changes from AND to an OR with bubbles on the input. We're going to use that to our advantage when we start to do schematics. So let's go both ways. If you push the bubbles through, the OR becomes an AND shape. And if you push it back again, the shape of the gate, the functionality of the gate, switches to OR if the bubbles are on the other side. Same thing over here. I can push, and the NOR gate becomes an AND gate. I can push it back, and AND becomes NOR. All right, so there's this symmetry involved. All right, so hopefully that gives you a good intro to Boolean identities. We'll use Boolean algebra enough where I think all these things will become second nature.